To set the stage, we are a technology that is already in buildings. We've been proven. We're now dancing with investors and partners and going to market in 6 large cities in the U.S. My background is on the electric system side of the meter. I can take you several decimal places deep. I would say a remarkable accomplishment, the electric system. I got introduced to large commercial buildings in the late 90s. I could make the same comment about those. I think, again, remarkable engineering feats. But back then in the late 90s, we got this idea, what if we took the meter out of the middle and allowed the 2 control systems to talk directly to each other? We concluded that we would dramatically change the operation, the design and operation of both my electric system and the commercial buildings. So I went looking for somebody that knew commercial buildings as well as I knew the electric system. That turned out to be Dr. Gregor Henze at the University of Colorado Boulder. He's still my co-founder and business partner. We decided that we were not interested in developing his IP or my IP. We didn't want to go down the same path as his peers or mine. So we said the only IP that counts is the stuff that we're going to now develop jointly. I'll start with this graph. You'll see some more of this graph. This is the electric load for the Willis Tower, 4 million square foot Willis Tower in Chicago. Used to be known as the Sears Tower. On the y-axis is the total electric consumption, cumulative electric consumption over 4 months. On the x-axis is time. I highlight thermal mass because that's the dynamic, the building dynamic I'm going to focus on today. I call it a battery because most people know what batteries do. Brad calls it a thermal flywheel, and that's probably technically more correct. Gregor and I had a lot to learn. We'll leave it at that. A lot of acronyms, but here's the result. We develop a high-fidelity model of each of these buildings. We wrap a multi-objective optimization algorithm around that model. And every day our platform sends a strategy to each building that best uses the thermal mass, the storage in the thermal mass to achieve those objectives. The lighter blue and the white at the top, that's the HVAC load that we controlled. The rest of it's lights and elevators and other things that we don't have anything to do with. As you can see, most of our strategies involve charging the building up at night, charging up the drywall and the concrete at night, and displacing energy during the day. You see that we charged over 4 months, we charged the Willis Tower up to the tune of an extra 600 megawatt hours. It's a lot of electricity, but we displaced 1,500 megawatt hours. Now, we all know that you can't have more than 100% efficient storage, so you're wondering. But remember, there's a lot of dynamics going on. You all know that running your air conditioner at night is a lot more efficient than running it during the day, and there's some other things that we take advantage of. In a typical building, we'll reduce the cooling expense and peak demand by 30%, and the energy use by 15%. And there's more, like that advertisement at night. Remember, I'm displacing cooling load during the day when I have my least efficient generating units at the margin. I'm displacing cooling load during the day when I have my highest electric prices. And in the Midwest, we get a bonus, goes back to the oil embargo days. We have very, very low electric prices at night. They often go negative. And yes, that means they pay you to run a chiller at night in the Midwest. It's happening more and more around the country. I like batteries, but we have some advantages. Remember my storage medium, the drywall and the concrete, the desks, the books, it's free. I don't have any space requirement. I don't have any building codes. I deploy in a couple, 2 to 4 weeks. The last one I like best, the drywall and concrete doesn't wear out. It just keeps working. This is all automated in the cloud. We get weather feeds from NOAA. We get price feeds from the electric grid. We send control strategies to the building. We get status information back from the building. There's the Willis Tower that you saw the information for. We've deployed in other very large buildings. These are all 1 million square feet or larger. The building on the far right is FAA headquarters at 1.6 million square feet in Washington, D.C. And this is why we're in it. It's nice to save buildings some energy and expense. We have some global implications, we think. My favorite is the financial risk management. We believe that we can risk manage price volume risk for a building, for a portfolio of buildings, for an entire city. My engineering team is highest on the carbon. We think that buildings, not coal plants, ought to be the focus of most of the discussion. We think we're the low-hanging fruit when it comes to GHG reduction. Thank you very much.